Today we're going to see that every knot bounds a surface. So what do I mean by that? If you take the unknotted knot, you can see that it would bound a disk, right? You could imagine, oh, I don't know, you could drop this into like a bucket of soap. I wish I had soap. And when you pull it out, it bound a nice disk. And so here's your unknot, and it would bound a disk. So it bounds a disk. Well, how about some other knot? What if you took, here's our familiar trefoil, the threefold symmetry. Does it bound some kind of object? And so we can think about it. Let's draw the trefoil. Here we go. What kind of thing would he bound? And well, you might think, does it also bound a disk? A disk that's knotted up somehow? But you can probably convince yourself that if it did bound a disk, then you could pull it into the disk and you'd end up with an unknot. Right? If this bounded some disk, if you had some knot somehow bounding a disk, then you could just move your knot inward into the disk and end up with an unknot. But we know that the trefoil is not an unknot, so it doesn't bound a disk. So we have only the unknot bounds a disk. So what is the trefoil bound? Well, we'll come back to this question in a few minutes. But first, let's think a little bit about surfaces. So I want us to think about surfaces and what kind of surfaces there are out there. And then we'll come back and see how that relates to the questions of knots. So when I talk about a surface, I mean two manifold, something that locally looks like two-dimensional space. And in particular, I'll say a surface, I'm going to limit my attention to surfaces that are closed. That means that they're compact. They don't go on forever. So they're not like the plane that goes on forever. It's compact. We'll limit ourselves to surfaces that are orientable. And surfaces that are without boundary. So let's do some non-examples. We said compact. So the plane, for instance, is not compact because it goes on forever. Orientable, what would be a non-orientable surface? Something like the Klein bottle. Why is it not orientable? Because you can't tell the difference between the inside and the outside. If you're an ant and you're walking along the outside, you could end up walking along and you'd find yourself in the inside. So you can't discriminate between the outside and the inside. So a Klein bottle is an example. Or, even simpler, you take a piece of paper, give it a twist, a half twist, come around, tape it to itself, and you get the Mobius band. And the Mobius band is another surface that has only one side to it. It's not orientable. If you trace around it with your finger, you find yourself on the opposite side. So it's one-sided, it's not orientable. You can draw a picture of the Mobius band like this. We just gave it a little half twist. So it's just like a cylinder with a little half twist. This is not orientable. And then we said without boundary. So, well, this one has a boundary. This one, so this has boundary. you can run your finger along the edge of it. The plane has no boundary, so the plane goes on forever, so it has no boundary. And so we just want something that has no edge to it. Okay, if we limit ourselves to these surfaces, then we have a really nice classification theorem. And so we can classify compact, orientable surfaces without boundary. And here's how the theorem goes. It says one of these surfaces is the sphere. Notice the sphere is a nice ball-like shape. It's compact, doesn't go on forever. It has no boundary, you never get to the edge of it. You never fall off the end of the earth. And there it is, that's our condition. So it's a surface. Well, there are other surfaces you might think of. We can build one. You can imagine something like a cube. A cube also has no boundary. You can kind of round out the corners if you want to avoid sharp edges, but here's a nice cube. You never fall off, you can go around it, and it's compact. And so you also have things like the cube. But what we're going to say is that the cube and the sphere are the same up to their equivalent, up to homeomorphism. And so when I say homeomorphism, what I mean is there's a bicontinuous mapping between them. There's a way to naturally map the sphere onto the cube or the cube onto the sphere. You know, you would just take the top part of the sphere and it would go to the top of the cube. And this right would go to the right of the cube, etc. So this means that there's a nice bicontinuous map. And as you start thinking about more surfaces without boundary, you might think of like the Mickey Mouse surface. So it's like Mickey, he has like a big ear, another big ear. He's kind of round, but he also has these big old ears. Notice the Mickey Mouse surface is also bicontinuous to the sphere. You would just take this portion here, be mapping onto here. It's kind of like you're taking this, you're kind of inflating it out. It's like Play-Doh, you're kind of stretching it out, stretching it out. And there's a nice continuous way to do that. So these are all equivalent. And anything you might make like, oh, you can make a tetrahedron, but it still has this basic like ballness to it, this basic sphere-like structure to it, where you can imagine how you'd map a ball onto a tetrahedron. Okay, so there's these. So the question is, are there surfaces that are fundamentally different? That's what a classification theorem is going to say, and it's going to say, yes, in addition to this family of surfaces, there are also surfaces like donuts that are fundamentally different. So this is a torus. It's just a donut. And the thing about a donut is there's no way to map a ball onto it. You know, you might kind of start by trying to map him onto here, but it's like here you have like some end, and here it keeps going around. And so these are fundamentally different surfaces. These are not homeomorphic. There's a dividing line between them. Now, there's other things this is homeomorphic to. The most famous example, oh, I didn't bring one, but it's a coffee cup. Because this, you can imagine this is just the handle of your coffee cup. And then, or where is the cup? Where you start pushing in on one side, make a little dent, and that becomes the cup part of the coffee cup. But you could also imagine taking something like a torus, a nice torus, and then what you could do is you could knot up. So you could take this part right here, and I can try and knot it up. Let's see if I've done this well. And as I knot it up, there we go. I've knotted up the torus. So yeah, it looks kind of crazy. But but there's still a nice continuous way to move from the torus to here, right? Like you could imagine like you could map this part onto here, and then you would map, you know, as you go around, maybe like, then you map like this part of the torus like onto here, and you keep going around the torus, tracing this out. And so there's a nice bicontinuous mapping. So these we think of being the same. So though the torus can look many different ways up to homeomorphism, these are all fundamentally the same thing. And they're all different from anything homeomorphic to the sphere. The question is, well, is that it? Well, no. If putting this hole in it is what made the difference, we can just do that again. So another class of objects would be what's sometimes referred to as a two-hole tori, a torus of two holes. It's like, what would this be like? It's like an inner tube for two people, right? These are holes in it. This is a hole that goes through it, right? This goes through it. These are holes that go through it. That's the key idea. And so it's fundamentally different from this object. And you can continue in this way by just adding more and more of these holes. So if you add more and more and more holes, you end up with, you know, in general, some tori with maybe, I'll say, G holes. So this here is a torus. This is a two-hole torus, and here we have a G-hold. Torus. So why G? G is a suggestive letter. G is going to be because we call these holes the genus. So this guy here has genus G. And this guy here is genus 2. It's like genus is places you can reach your hand through and grab onto it. You can go all the way through. This guy here is genus 1. And our original sphere, these all had genus 0. The genus was equal to 0. Okay, and that's it. The classification theorem tells us these are all of the surfaces you can have. At least all the surfaces that, it's like where did this show up on the list? Well, it's not there because this is non-orientable. So this is all of the orientable, you know, where's the plane on the list? Well, the plane's not there because it's not compact. It goes on forever. So this is all of the compact, orientable surfaces without boundary. This is all of them. Okay. So this is pretty nice to understand these. I'll mention a really hard problem is trying to think about, well, can you try to classify, these are two-dimensional surfaces, can you try to classify three-dimensional and four-dimensional spaces in a similar way? So it's quite nice that we have such a classification, because in higher dimensions it doesn't come out quite as nice. Okay, but we have this, and so let's begin thinking of what's going on here. Euler, this was Euler's insight. Euler's insight is if you take anything that looks like a sphere, like this cube, anything homeomorphic to the sphere, he says you can count the number of faces it has. So you can count the number of faces it has. So like here we have something with faces, 6 of them. It's a cube, front, back, side, top, bottom. You can count the number of edges it has. 4 along the sides, 4 on top, 4 on bottom, so it's 12. You can count the number of edges it has. You can count the number of vertices, the corners where the faces and edges meet, 4 in front, 4 in back. So if you count the number of vertices, there's 8 of them. And Euler says, notice, faces plus vertices is 2 bigger than edges, 14 versus 12. And it's not just for this one. He says, look at anything. You know, look at this little tetrahedron. We have 4 faces, 3 triangles on top, 1 on bottom. 4 faces. We have how many edges? 3, 6. 6 edges. We have how many vertices? 3, 4. Again, the faces plus vertices is 2 more than the number of edges. And he says, build whatever you want. Get creative. And whatever you build will have this property, as long as it's homeomorphic to a sphere. I could just throw them together like this, and here I would have another thing that satisfies the same property. And so you could write it like this: faces plus edges is 2 more than edges. Faces plus vertices is 2 more than edges. So faces minus edges plus vertices is 2. Okay, let's go ahead and prove that, or at least try and get some intuition for why it's true in general. So anything that can be expressed as a sphere. So here's one way to see that. Well, take a sphere. This is like a proof by induction. And imagine you just have 2 faces. So imagine your number of faces is just equal to 2. Then, so you have some face on top and some face on bottom, and they would meet along some equator there, but that's probably broken up into like edges and vertices. And I don't know how many edges and how many vertices it is. It's whatever number. But notice along that equator, the number of edges, 1, 2, 3, is equal to the number of vertices, 1, 2, 3, because they form a circle. So edges equals vertices. So as long as you have 2 faces that make up your sphere, then edges equals vertices. So then, of course, faces minus edges plus vertices is 2, because these are the same. Okay, but we've only proven there are 2 faces. What if you have more faces? Okay, good question. If you had more faces, well, maybe you have, some guy that like comes up and breaks this up into a couple faces. But notice what I've done. In order to break this up into a couple faces, I added an edge, but I also added a face. So you add edges and faces together. So the count of faces goes up by 1, but so does the count of edges go up by 1. So what does that do to your 2? Well, you increase your faces by 1, so you get plus 1. Your edges increase by 1, so it's minus 1, and so it's still 2. And so as you add more faces, they come by adding edges, and they're just going to cancel out. And you could do other things, like you could break up an edge by adding a vertex, but now I've added a vertex at the cost of this one edge broken to 2 edges. And so I've increased the vertex count and the edge count, so they cancel off. So it remains true. And so you can do a quick little proof by induction to see that this is true for anything homeomorphic to a sphere. Okay, what happens when we move over into this setting? And now we want to say, what is faces minus edges plus vertices? It's like, okay, well, how could we introduce a genus? You might think that you have some surface, so somehow your sphere is broken up, and you have like faces connected to faces, connected to faces, and they kind of go throughout and make some sphere. And maybe you want to introduce a genus, but you have some face on the top and some corresponding face on bottom, which is then connected to other faces as well, connected to other faces. Be like, in order to make this, add some genus, I want to take this face on top and delete it, and take this face on bottom and delete it. It's like deleting the top, drilling a hole in the top of the sphere, drilling a hole in the bottom of the sphere. And then what I want to come and do is add some new faces and edges that connect that hole. So now I have some hole going through my surface. So then we can stop and we can think, well, what did that cost us? Well, we deleted 2 faces. So the number of faces went down by 2. And then we added some faces. Here is 4. Let's say in general this is some n-gon. It could be a triangle or a square or whatever. But let's say there were n faces we added. So then we added n faces. But then we also added the same number of edges. So it also came at the cost of adding n edges. So what is that going to do to this count overall? Well, the plus n faces and the plus n edges will cancel out because of this minus. And you end up just decreasing this count by 2. So instead of it adding up to 2, the new overall count will be 2 minus that 2, so it's going to be 0. So if you take any object like this, like a torus, and you can do it, and you break up the torus into little faces and edges, and you can kind of imagine breaking this up. So here's some rectangles you broke it up into, and you might break it up into a couple more. You can play this game, and you'll get faces minus edges plus vertices is 0. Similarly, we can come over here, and now what happens when you have 2 holes? Well, it's the exact same argument as before. We're just going to take some portion of the torus that kind of looks like a sphere, delete a section on top, a face on top, delete a face on bottom. That decreases the count by 2. Then you add faces, but you also add edges, so those cancel out. And so the overall count goes down by 2. And so here you'd have faces minus edges plus vertices is subtract 2. Subtract 2 from what it was, so from 0 it becomes negative 2. And now we're getting the hang of it. So each time you add a genus, it comes at the cost of subtracting 2 from the sum. So by the time you get to adding G genus G, what did you do? You subtracted 2 G times from the initial value of 2. So you would have that faces minus edges plus vertices is you start off 2, but then you subtract it off G. You subtract it off 2 G times. So in general, we get this relationship. Now it seems like this is a significant number, so we give it a name. We'll call this the Euler characteristic. We'll say that the Euler characteristic for a sphere or anything homeomorphic to the sphere is 2. And I'll denote it with the Greek character chi for characteristic. The Euler characteristic for the torus, or anything homeomorphic to the torus, is 0. It's minus 2 when you have genus 2. And it's 2 minus 2g when you have genus g. Okay, so now we've classified surfaces and we've saw what the Euler characteristic is. But let's come back over here and think back to our original problem. Well, here I want some surface, but I want it to have a boundary component. So this is a surface with boundary, right? It's a disk, it's a surface, but it has a boundary. The boundary is the knot. And so then our question becomes, well, what happens when you add boundary? So let's figure that out. We said in general, if you have a genus G surface, then this is your Euler characteristic. But what happens if you add some boundary component? What happens if, for instance, you were to drill out a little face here, giving you some boundary component? It's like you took a bite into this G-hole donut, right? Right? Like what would be the Euler characteristic now? So for each boundary component, you're removing a face. That's all you're doing. So this count will go down by 1. So if you had a genus G surface with 1 boundary component, then you would have, by your Euler characteristic, is 2 minus 2g, but then you remove the face, so minus 1. And in general, if you had B boundary components, so if instead of 1, this was just, if you had B boundary components, then you would be subtracting off B faces to get those B boundary components. It's like taking B bites out of this. And each time you removed it, you would get a boundary component introduced, and you would be removing a face, and so you would have this as your relationship. There's a minus B factor. So let's go look at knots. we want to think about what kind of surface does this bound? Okay. A couple observations. The first observation is that if a knot is the boundary of a surface, I'll give the surface a name. Let's call it sigma. Then we know that the Euler characteristic of sigma will be 2 minus 2 times the genus of whatever sigma is, minus, well, it has one boundary component, the knot. So minus 1. That's what we just showed. Okay, so that gives us some information about the surface. This is of course a surface that's orientable and compact. Okay, let's use that fact and start thinking about what kind of a surface might the trefoil bound. Now, when you look at the trefoil, you might be tempted to say, well, here's an obvious surface it bounds, and you might start filling in this part, and this part, and this part. So that seems to be a surface. There's one problem. What is this surface here? This surface is it's a band, but it has 3 half twists. So let's see what that looks like. It's a band with not 1 or 2, but 3 half twists. And then you can tape it together. Here it is. And it looks kind of wild. I guess it was a little bit, could have been longer. But if you follow it along, you can see with 3 half twists, you have the same problem with 1 half twist. It's the Mobius band and still. You can see it in the diagram quite nicely. If you start on this side, on the front, you would travel, you'd be on the back here, and then you'd be on the front, and then you'd be on the back. So it's a one-sided surface. So this is non-orientable. And that's going to be no good. We're not going to want to work with non-orientable surfaces, because a classification where we understand is we understand orientable surfaces. So let's throw this out, strike this, and try and see, can we find an orientable surface that a knot bounds? So how to find an orientable surface. This is going to be an algorithm that's due to Seifert. He gave us a way to do it. Here's what he says. He says, take your knot. So let me draw another copy of him. Take your trefoil. Something like that, and give it some orientation. Doesn't matter which way you go. So let me go this way. Okay, gave it some orientation. And then his rule is you smooth out the crossings. This is very similar to when you had Conway's algorithm, and he had the skein relation where you smoothed out crossings. So the rule is whenever you have a crossing, you look at the orientation and you smooth it out so that the in comes out, the out, the in comes out, the out, You keep the orientation, but now you've smoothed it out. So that's what we're going to do here. We're going to follow along here, but then we're going to smooth it out like this. And then we follow along here, but then instead of crossing over, we smooth it out like this. And then we follow along, and then we smooth it out like this. And then you can also do on the inner track. You get smoothed out, smooth it out, smooth it out. Okay. What do you end up with? On bottom, you have an irregular disk and another disk on top. And so you can visualize this as two disks. Like a big disk on bottom with another disk on top, a smaller disk on top. And then you said, well, that doesn't bound the knot. It's, these are detached. But there's one more thing we have here. We have these crossings. And Cypher's insight is, well, what this crossing really is it's just like a band that's connecting the bottom disk to the top disk. So this right here corresponds to some band that has a half twist in it that's attaching the bottom to the top. And so these bands, these are bands with half twist. It looks something like this, but all that is a half twisted band, where a band is just a long rectangular piece that you gave a little half twist to. And here we'd have not just one of those bands, but you have another band from this crossing. So that would correspond to some other manifestation of this. And here you have a third band that, is corresponding to some guy largely in the back. So maybe he looks something like that, except there's only one half twist. Something like that. So you have a disk on top of another disk with 3 bands attachment. Let's make sure that this is orientable. To make sure it's orientable, check it has 2 sides. So you might begin by saying, let's color this. Let's say that this is the shaded side is top. So this is the top of each disk. So the top side would be white. And now I half twisted some on the bottom. So that's black. But then I go under. So the bottom of this is black. So this whole thing should be white as well. So you see it has some nice two-sidedness to it. This is the top, this is the top. Here you have a two-sided disk attached with these half twists to another two-sided disk. This is a different disk right here. And we've constructed it so that this surface has as its boundary the original knot. You can recover that original knot. Here's the original knot. It's this guy right here. And so the incredible thing is, this algorithm works on any knot. And you can try and convince yourself why that works. Whenever you have a crossing, you smooth it out. Convince yourself if you smooth out all the crossings, you just get a bunch of disk. And then you can just add all the crossings back in with half bands. And do a little bit of thinking to convince yourself that it will end up being orientable. But it's constructed in such a way that you always end up with a nice orientable surface for your knot. But then here's the big question. What is the surface? According to our classification theorem, we know it's one of these. Well, no, it's not. It has boundary. So it's one of these with a boundary component. Right? It bounds a knot, so it's one of these with some boundary, so with a disk removed and maybe tied up in some way. But it's one of these with some boundary. And so the question is, which one? And so that's what we're going to try and do now, is figure out how can we understand what is the genus of the surface. But it's not going to be a mystery because we have this relationship. And it tells us if we can figure out what the Euler characteristic is, then we should be able to figure out what the genus is. So maybe right here, we can begin thinking about this. Can we figure out the Euler characteristic for this guy? So recall, Euler characteristic is just defined to be faces minus edges plus vertices. Now, this is made up of two kinds of creatures. One of them is a circle. You end up with these disks. And so what is the Euler characteristic for the disk part? Well, for any disk, it's like, okay, we could stick some edges and vertices on that, however many you want. Let's do 2. You could say it has 2 edges and 2 vertices, but then you just have one face with 2 edges and 2 vertices. So the Euler characteristic of the disk comes out to be just 1. How about these bands? Well, these bands, these half-twisted bands, it's just a rectangle with a twist in it, you know. It's just a little rectangle that we put some little twist in it. And you can think, well, what happens when you attach a band? So attaching a band does what to the Euler characteristic? Well, this segment here, the top and bottom of the band, isn't contributing anything because that vertex was already there and those edges were already there as part of the circle. So that was already part of the circle. So that would have already been counted when you count the Euler characteristic of the circle. So all you've done is added 2 edges and 1 face. You add edge, edge, and a face. So whenever you attach a band, you add 2 edges and a face. So it goes up by 1 but down by 2. So the Euler characteristic goes down by 1. What do you do to it? It goes down 1. Okay. Maybe I should write that by saying, when you attach a band, it's minus 1 to your Euler characteristic. So what that's saying is to figure out the Euler characteristic of a creature like this, you just count up how many circles you have. Since you have 2 disks, that's going to give you an Euler characteristic to begin with of 2. Euler characteristic 1, Euler characteristic 1. But then you attached 3 bands to it. From our 3 bands, it's just going to go down by 3. So the Euler characteristic of the surface is negative 1. In general, we can generalize this. What does each band correspond to? Each band just corresponds to a crossing. So you can say your Euler characteristic is equal to your number of cipher disk, or your number of cipher circles, the circles you get from the cipher algorithm, minus the number of bands, which is the number of crossings. Okay. Euler characteristic of this is negative 1. Why does that matter? This is why it matters. Because if the Euler characteristic is negative 1, I can figure out what the genus is. The genus of the surface is negative 1 equals 2 minus 2 times the genus of my surface, so let's call it G, minus 1. Okay, let's try and do some math. 2 minus 1 is 1, minus 2 is negative 2, divide by negative 2 is 1, so your genus, that's not right. Yeah, your genus is 1. And so we know that this surface right here is a genus 1 surface. It doesn't look like it. It doesn't look like a torus. But the claim is that this is secretly a torus that has a boundary removed, one component removed, given to one boundary component, maybe tied up and embedded in some interesting way. And so this, now we know that the trefoil secretly bounds something of genus 1. This is incredible. So let's generalize it. What did we just do? We said that the Euler characteristic is the number of Seifert circles minus the number of crossings. Let's get some color. So let's just call that C. I'll just call this value here C. No, I guess the number of crossings should be called C. So let me call this S for Seifert, the Seifert circles you get. Then you have that Euler characteristic is your Seifert circles minus your crossings. But we said that the Euler characteristic is 2 minus 2 times the genus minus 1. So putting these together, you get that your number of Seifert circles minus your number of crossings is 2 minus 2g minus 1. So I guess that makes that a 1. So then you get, you can subtract off that 1 and divide through by that negative 2. And you get 1 plus C minus S over 2 is your genus. I think that worked out. Where C is your number of crossings, and S is your number of Seifert circles. Okay, very good. Well, maybe we should do another example. No, let's say this. This is the genus of the surface. We now have the way to find the genus of a surface. Now what we want to do is we want to definition, the genus of a knot. We want to define the genus of a knot. Just like how we defined the determinant of a knot by defining the determinant of some matrix associated to the knot. And so you would want to say, well, just define the genus of some knot to be equal to the genus of the surface. But there's a problem. See, this surface involved a choice. You started out with some diagram for the knot. And the question becomes, if we started out with a different diagram for the knot, and we repeated the process, well then you would follow Seifert's algorithm, and you'd get a different genus possibly. And so how do we know you get the same genus for every diagram? It turns out you don't. As you distort your diagram, you could, you can see this even, like look at the unknot, right? Like the unknot bounds this guy, this disk, which has genus 0. But the unknot also bounds this dumb surface, the one that comes down and has like a little donut thing going on, right? And so like the unknot bounds both these surfaces. This one has genus 1, this genus is 0, and this genus is 1. And more than that, you could make an unknot that bounds, oh, heaven forbid, you could have like a bunch of genus in there, like 3 genus. It's like, so this is like a torus a donut you bit out of, and this is like a 3-hole donut, like a bite out of it. It's like, which one should you call the genus of the unknot? It's like, well, this definition wouldn't know it. Well, obviously, you should say, well, that's all extra, that's not necessary. We should pick the smallest one possible. And that's exactly what we do. We define the genus of the knot to be the minimum of the genus of sigma over all possible sigma that have boundary k. So you consider all the surfaces that have sigma, that also all surfaces that have k as its boundary, and you find the smallest genus, and then you know that's the genus of your knot. Well, that gives us a problem though. What is the genus of the trefoil? We've only shown that the genus of the trefoil, the knot 3, 1, we just know that it's, well, for one particular example, it came out to be, what was it, 1. In this particular example, it was 1. But there might be something else where it's less than 1. So we've only shown the genus is less than or equal to 1. Because it's the minimum of all possible. And so we found one candidate that's 1, but it might be smaller than 1. But here's the key insight. What would it mean if it had genus 0? Well, think through it a little bit. Genus 0 means you're the sphere. And you're not just the sphere, you're the sphere that with some boundary taken out of it, which leaves you with just a disk. So if it was genus 0, it'd be the disk, but only the unknot, we said, bounds a disk. So only the unknot has genus equal to 0. And therefore, since we know the genus of the trefoil is at most 1, and it can't be 0, because the trefoil is not the unknot, we can conclude the genus of the trefoil is actually equal to 1. Very good. Let's do another example. Let's consider the knot 5, 1. So where is the eraser? This will work. Let's consider the knot 5, 1. This is a knot with 5-fold symmetry. Oh, let me get a picture to make sure I draw it correctly. Yeah, okay, we can draw this. So let's consider this star-like knot. Okay, this is the knot 5, 1. And we want to figure out what is the genus of this knot. So how do we do that? We begin by giving it some orientation. And then we're going to smooth out these crossings. So this gets smoothed out like this. This gets smoothed out, smoothed out, smoothed out. So, and then on the inside, you can smooth it out. So notice what you get. You have a disk on the bottom, big disk on bottom, and then a smaller disk on top of it. And then, what do we do at these crossings? Well, we say those crossings are like little half bands that we're getting attached. Another little half band. Another little half band. Another little half band. Another little half band. So you end up with 5 of these. I don't know if I can draw 5, but here's 3. We'll do 2 in the back, I guess. It's 2 disk attached with 5 bands that correspond to the 5 crossings. Okay, so we can go and through the whole process again, but let's just jump to our algorithm. We ended up with this algorithm where we said the genus of the surface is 1 plus the number of crossings minus the number of of circles all over 2. So how many crossings? 5 crossings. So it's 1 plus 5 minus the number of circles, which is 2, 1 on top, 1 on bottom, all over 2. That's 4 over 2, which is 2. So then what is the genus of 5, 1? Well, you want to say it's 2, but all you can conclude is that it's at most 2. Because there might be some other surface for some other representation of this knot that is genus 1. Well, we know that 5, 1 is not equivalent to the unknot. How? We could look at the Alexander polynomial, the determinant, or colorability, or one of many ways to see that. And so we're down to 2 possibilities. He's either 2 or he's 1. We know that it's not 0, since 5, 1 is not the unknot. Okay, so what we need is some kind of lower bound. And we have one. So this gives us a method to get the upper bound on the genus. But how do we know if it's actually 1 or if it's 2? An incredible result. The genus of a knot turns out to be related to the Alexander polynomial for that knot. And what's the relationship? Well, the genus is always at least as big as half the span of the Alexander polynomial. What do I mean by span of Alexander polynomial? Well, let's just do it with this example. For 5, 1, here, I looked it up. We can calculate this from our last lecture. We know how to calculate this. The Alexander polynomial for the knot 5, 1 would come out to be something like t squared minus t plus 1 minus t to the minus 1 minus t to the minus 2. But you remember that when we write these, we write them up to multiples of t. So someone else might have calculated it and using a slightly different diagram or something, may have gotten something like t to the 4th multiplying through by t squared minus t cubed plus t squared minus t minus 1. So it's like the polynomials aren't fixed. They're up to some multiple of t. But that's okay, because all span means is when I say span is the difference between the highest and the lowest coefficient. So here, like my span would be 4. Same thing here. The difference between 4 and 1, which is 1t to the 0, is 4. So my span of this guy is 4. My span of the Alexander polynomial of him is 4. So according to this formula, for my knot 5, 1, I know the genus of the knot 5, 1 is at least as big as half of 4, which is 2. So the genus is at least 2 by this relationship. But the genus is also at most 2. And hence we can conclude the genus of this knot is actually equal to 2. Let's look at one more example. Come back to the trefoil. We said that the genus of the trefoil is equal to 1. I mean, we can do the Alexander trick here. What is the Alexander polynomial for the trefoil, for 3, 1? I wrote it down because I forgot it. But we calculated last time, it was something like t to the 1 minus 1 plus t to the minus 1. Or maybe you wrote that as t squared minus t plus 1, or however you write it. But the span is always going to be 2. So the span of 3, 1 of the Alexander polynomial for the trefoil is 2. And so by a relationship, the genus of the trefoil is at least as big as half of the span, so it's at least 1. There's another way. And then we showed that for a particular surface it actually equals 1. So therefore we know that it's also smaller than or equal to 1, and hence you can conclude it is 1. So this is a very powerful technique. Now sometimes you won't be able to, maybe this is too small of a lower bound. The example you find will still give you some range. But between these two tricks, between this guy giving you a lower bound and constructing an explicit surface and calculating its genus to get an upper bound, you should typically be able to narrow it down quite a bit. And for small examples, it's usually good enough to figure out exactly what the genus of the knot is. And this genus, it's a knot invariant. Like how do you know it's a knot invariant? Well, by definition. We defined it to be the minimum of all possible surfaces. So it has to be invariant. It's change the surface doesn't matter, because that always comes into the definition. Okay, I want to show you one last thing with genus. It's a really, really cool application, and it's something that you can use at like fancy dinners or like less fancy dinners to impress people. And so let me introduce the question. Here is a knot. And the question is, can you cancel out the knot by combining it with another knot? What do I mean by that? Well, here's this knot. You kind of captured the knotedness. And here I have like the unknot. And you might say, what happens if I combine them? And to combine them would be like merging them together. With glow sticks, it's quite nice. You can just pop it open. And you can merge them together. And you're like, oh, dang it, the knot is still there, right? When I merged it with the unknot, I just made it a bigger knot. So it's still knotted. So okay, maybe that wasn't the right move. So let me break these apart. But then the question becomes, well, can I merge this with some other knot? So let me like tie this into a knot. Now this one's knotted and this one's knotted. And is it possible that when you combine these knots, oh, this is quite knotty. When you combine these knots, you'd get, well, let's see. Is it going to happen? I'm combining this knot with this knot. Am I going to get something that's not knotted? It's like, well, it looks pretty knotted, and you can try and play around with it. And, oh, I don't know. I mean, you can try, but it still seems pretty knotted. You might imagine it's Christmas time, and so you go into your attic, and you have some Christmas lights. And of course, what you do with Christmas lights is you take the two ends and you plug them together, and you plug it into itself. And now you've captured these knotted up Christmas lights. And you're like, I don't want to unknot that. Does there exist some other knotted up thing of Christmas lights? So I could combine them, and suddenly it would become unknotted. That is the question. It's a very natural question to ask. I ask it every year when I decorate. Well, I stopped asking it because now I know the answer. So here we go. We have some knot. I don't know. I'm going to try and draw. I'm just going to say it's knotted up somehow like this. It's something that's knotted up into some mysterious K. And then I had something knotted up into some mysterious J. And then what we did was we connected them, and we made them a single knot. I call this the connect sum of the knots. So this would be denoted by K, connect sum with J. I guess we should see an example, right? Like, let's do an explicit example. Here I have a trefoil, and I can have some other trefoil over here. And then what you could do is you could merge them together by connecting them up like this. And then you get the trefoil connect sum itself. So that's what we mean here by combining two knots. And our question is, can we ever get knots to cancel? Can we ever find, question, when does K combined with another knot come out to equal the unknot? to answer this, let's think about genus. How does genus play with connect sum? So I'll write this as a proposition. If I have the genus of K1 connect sum K2, what is that going to come out to be? Well, one way to think about it is, here's my trefoil. I can find some surface that this trefoil bounds, like before, and I can pick some surface so that it has genus 1, because the trefoil has genus 1, so there's some surface that bounds with genus 1. Also some of genus 2 and 3, but there's something that has a genus 1. And here's another copy of it. And so this is also going to have genus 1. And then all you have to convince yourself of is when you combine these, you haven't changed the genus. And so convince yourself you don't change the Euler characteristic. All you do is you combine them. So that the whole thing of this surface would have genus 2. So now I've given you a surface, this whole thing has genus 2. Because it's genus 1, merger of this genus 1. So it's like if you combine two donuts, you get a donut that has 2 holes in it, so it's genus 2. So exactly analogous to that. But that's just one possible surface. Maybe there's some surface here that a smaller genus surface for this combined knot. So we just know that this guy has at most the genus of the first guy plus the genus of the second guy. So that's what we've argued so far. But you can think about and convince yourself, actually, these come out to be equal. Because if you have some surface that bounds K1 connects some K2, you can break it up into two surfaces that bound that bound K1 and that bound K2. And so you can show that the inequality has to go both ways, and so in fact this is equal. It takes a little bit of careful geometrical argument, but these come out to be equal. Hopefully that's believable. But notice what that means. Recall, the genus for the unknot, we said comes out to be 0, and the genus for any other knot where k is not equal to the unknot is strictly bigger than 0. It's at least 1, right? It's at least 1. So what does that mean? Corollary. Well, if you want this connect sum to come out to be the unknot, if you want this connect sum to come out to equal the unknot, if you want this guy to actually be the unknot, then the genus of him has to be the genus of the unknot, which is 0. So then what did the genus of K1 and the genus of K2 have to be? Well, these are going to be positive if it's not the unknot. So they can't be anything other than the unknot, otherwise it would be positive. So these must both be the unknot in order to come out with genus 0. You must have, that would imply that K1 and K2 must both be unknot in order for this to be 0. Or the unknot. That is, we just showed that K1 connect K2 equals the unknot precisely when, if and only if, K1 and K2 are both the unknot. So back to our original question. When can you get K and J to cancel to get the unknot? Never. Unless you started out with two knots that were the unknot. But if you start out with some knot that's not the unknot, so let me recover my original knot. If you start out with some knot that's not the unknot, then there's nothing you can combine it with to get the unknot. There's no way you can combine with if you combine with another knot, it just gets more knotted. It has bigger genus. So there's no way to get it down to genus 0 to having it be the unknot. Well, at least that's the case in 3-dimensional space. In the future lecture, we'll have to move into a 4th dimension in order to change the rules of the game. But that's a story for another time.